So first I'll introduce you to the primary tool I use in my workstation to explore the Tango data sets and show you what it's become capable of lately. It is a web-based tool. It's a next-generation web application, so it bothers the workstation excessively. It's currently consuming about 1.5 gigs of memory in Internet Explorer and about another 3 gigs in the server and the worker process. In any case, this here is where I can pick sessions from the database. It basically gives me a list of all of the sessions arranged by date or a name if I've given it to them. The top left display shows me the three-dimensional data, the point cloud that was received from Tango at a given point in time. The image shows me the picture that Tango was seeing at that point in time, or a relatively close picture. The bottom left shows me the mesh that was generated from the point cloud using Delaunay triangulation. I have to make a shout out here to the Triangle project and especially triangle.net. That's a seriously slick piece of work. Finally, over here is the culmination of the effort, which is the textured mesh. So it took this image here, this mesh, and smashed them together and tried to come up with something useful. Finishing up the explanation, up here are basically global controls for system operation. These three guys show how the data is aligned. In other words, the fact that the cloud and the magnet are both green means that this cloud has an exact pose. The magnet is what I use to represent poses. So it means this cloud, basically, it got a pose for this cloud at this time from Tango. The red image means it didn't get an image from Tango at this exact time, so the image selected here is the closest possible one. This is pretty much par for the course with Tango. Almost always point clouds and poses are aligned. Almost never images and poses are aligned. And there's some interesting things to think about with respect to that too, that I'll go into in a later point. Really quickly, you can't actually ever see the picture where it got the point cloud from because the picture's all messed up with a pattern in it. This is a test which nobody cares about. These two arrows let me go forward and backwards. If I click on the pose, I'll go forwards and backwards by poses. If I click on the cloud, I'll go forward and backwards by cloud. The reason that that's there is because there's about 3 to 5 times as many poses as there are clouds, and that allows me to check out quickly the cloud pose synchronization in a particular data set. Here, this indicates whether or not I am rendering pictures. I actually always am. I've just never fixed this. Likewise, this indicates whether or not I'm rendering clouds. I always am, and I've never fixed this. These two work. This one indicates whether or not I'm generating a mesh, and this one indicates whether or not I'm generating a textured surface. They're both green now because they are, in fact, turned on. The operation's about twice as expensive as it needs to be because of the fact that it does it all over again each time. But all of my interests right now are over data accuracy. They are not over optimization. I'm worrying about optimization next. This determines whether all of the cameras are locked together, and they are right now. That's why it's green. So if you see as I rotate this image a little bit, all of them move in unison. Down here, the paperclip, when it's green, it means I want to accumulate point clouds. It'll, as I go through each new one, it'll keep stacking them up on top of each other. This will align the camera position with the point cloud position. This is used when I'm not locking the cameras together, and the lock icons basically allow me to say, okay, take this guy's camera position and copy it to the two other guys. So anyway, that's the basic interface, minus a whole bunch of other junk lying around. And in the next cut, what we'll do is go through what we're actually seeing in this scene. Okay, first let's look at the good. If we look at this image here, we can see that Tango has definitely acquired the shelf here, and it's in the foreground. Likewise, it's acquired the foreground of the picture image here. And if we look at the mesh, we will see that that information is there. Now, my picture frame isn't as lumpy as the mesh, but it's done a pretty good job. And when we look at the texturing of it, we can be very pleasantly surprised by the bottom of this shelf. And the reason is because all of the data needed to mathematically solve this problem is there. And so with respect to, the noise in the Tango data, that problem is solved. The texture is well applied to the bottom of the shelf. The registration of the texture, even with the edge supports, is reasonably decent, given Tango's resolution of those edge supports in the first place. And so this is pretty pleasing. And it would be wonderful if we could go through life with our Tango devices expecting them to come up with these wonderful planar surfaces and, really pretty good registration on the model. As we're going to see in the next sections, things go from bad to worse. Alright, before I start digging into some of the messier details, I do want to say that overall I'm exceptionally pleased by the work that Google has done. I think it's a very high quality, and none of these observations should be taken to mean I'm anything but quite enthusiastic about the Tango platform. I'm simply realistic. A lot of these issues are ones we as Tango developers are going to have to address on our own because they will require heuristic solutions. And not even an organization as mighty as Google can come up with a heuristic solution that fits everything it encounters. Alright, so let's start looking at why I really would like to communicate to the Tango community that racing hell-bent to build a mesh out of the data is not a good idea without first looking at the data as a statistical entity. We looked before and we saw that when things work well, things work very well indeed, but now let's look at some issues. The first to look at is this spike that's right here. You can see several of them in the mesh because you can see through it. But if we concentrate on this one, you'll see that there are some green dots up here. Tango is rightfully subject to artifacts in its visual field, just like we are. I mean, I got floaters in my eyes. However, those need to be filtered out before you go build a mesh, otherwise your triangulation routine is going to gleefully make a spike in the middle of your mesh where it's obvious that one shouldn't be made. That's a perfectly obvious thing to do. You may ask why I haven't done it. My goal at this point in time is to have accurate transmission and reproduction of data across, let's say, the Android tablet running OpenGL, the Android tablet running WebGL, Windows doing it all in its head on the server, the workstation doing it in WebGL and some in C++. So there's been a lot of matrix change to make sure that we're accurate. So for that reason, I haven't applied data filtering because I really do want to know exactly what I'm looking at before I start messing with it. My fundamental philosophy in life is that you should not begin fiddling with data that you do not understand. All right. One thing to point out here is you'll notice this speckling pattern in the image. This is deliberate. What I've done is I've set this image up as flat shaded. In other words, the surfaces are not smoothed, and I have lit it with a strong light from the side. What that lets me do is to see that my surface is anything but uniform. You look at the point cloud here and you're like, oh, Tango, it's found a wall. Isn't that obvious? My brain says wall, the picture says wall, but as you rotate it around, Tango has actually found the probability of a wall. All right, so that as you're looking at it from this side, you basically can see that it's not a wall that Tango's giving you so much as this slightly spiky surface. All right. A lot of this can be addressed by various smoothing operations. However, I think there was a dude who posted in Stack Overflow was asking a question about R, and he basically didn't know what resources in Android apps were. But I've been thinking ever since, R, the language, may be our best friend for doing initial processing. The reason being, I have a strong suspicion that if you look at a wall just as a blank feature set, all right, and you do a statistical analysis on it and yank a couple of roots out of it, what's going to happen is you're going to come out with a wall. Basically, you're going to get the two axes of the wall. But what that's saying is that just because you have the point cloud of a wall does not mean it's a good idea to feed it to a rasterization or a triangulation routine. All right. Now let's move on to where things get even more problematic. If you look up here, it's the top of the shelf is bizarre. All right, and the reason is because mathematically what we have is rays that the ones that pass the lip of the shelf have to be heading in an upward angle, I'd say, of, I don't know, 45 degrees or better. So there is literally no information here, and the rasterization routine is basically guessing. All right, so what it's ending up doing is stepping the shelf down gradually until it's finding wall intersection points. However, the point cloud isn't handing it too many of those, so it's basically just carrying the shelf up to a level that it shouldn't. In the next scene, I'll show you where this can get considerably worse. One thing to keep in mind here is that the algorithms that allow me to do this triangulation, it's based on what's known as Delaunay triangulation, has to work on a 2D planar surface. All right, when you get into trying to do Delaunay triangulations and multiple simultaneous Tango point clouds, you're going to need to bring other stuff to the party because you can't do the triangulation algorithm on things that are overlaid on each other. It gets into a mathematical principle called manifold surfaces, and trust me, you don't want to know anything about them. Those of you, by the way, who are writing your own triangulation routines, I strongly recommend you pick up Triangle or triangle.net and use that. I know about writing triangulation routines, and I believe that Triangle means that I never ever have to go talk to an edge algebra again for the rest of my life. And I consider that to be a significant improvement on my quality of life. If you've never met an edge algebra, you probably don't want to. But closing up on the bad is that you have to remember that all of the data you need isn't always there, and the mathematical routines that operate on that data, what are they going to do when, there isn't enough information for them to finish up their job? All right. All right. Now we'll move on to the ugly. This is a still life with Tango test I have set up with various artwork I've collected in my dining room. It's probably a good thing I'm single right now. Otherwise, whoever I had for a girlfriend would have killed me for certain. For the record, this is Victor. Basically dude with fish coming out of him everywhere. And this is my mascot, definitely my Tango Project mascot, the flying pig. And this is a candlestick, which it turns out Tango hates, and with a passion. Now, if we look at the 3D textured mesh, we can see Victor's eye registered here. We can also see correspondence with the texture there and there and there. The fish seems to be well textured, and the dark areas of the window frame seem to be registering fairly well. Um, there are some spikes from visual artifacts appearing here, and once again, of course, that we can see that the table surface is not smooth. However, we weren't going to talk about small artifacts, we were going to talk about big artifacts. Big artifacts is that the system doesn't have enough mathematical information to know what to do about information that simply isn't there. In other words, it can see the table, it can see the front side of Victor, but the back side of Victor it can't see. It can't see any of this, and it can't see basically on about a 80-degree angle or less. It can't see anything in the way to the floor. So what happens when the math routine goes to work? Well, that's when things get very interesting. Let me see if I can orbit this around so you can see it. This is slightly problematic only because, there we go. The system is zoomed into its max. I'm not going to claim I'm a huge fan of the orbit controls. Alright, it's done the best that it can to know what to do with the geometry set, but basically what's happening, as you see, is it falls away sort of a 45-degree angle for the edge of the table, because that's the other data. So it's got Victor's head, it's got nothing here, and it's got the table here. So it's just sort of yanked it down to a 45-degree line, and if it wants to be agreeable and let me keep dragging the image around, you're going to say that that ridiculous process continues ad infinitum. It's not a math error. It's doing the best it can with the information that it has. Now, I can go to the triangulation mesh and tell it what I think are the actual boundaries of the objects. In other words, if there is a high Z discontinuity, I could say this is a boundary, please don't try and stitch it together with other triangles. However, the decisions about when you're going to apply that heuristic and under what conditions are not as easy as you might think. Recapping, my only point would be to those who have been out chasing, generating mesh surfaces, I would argue you first want to think about Tango in terms of statistical probabilities and statistical processing. After that, absolutely, you want to fling all of the data into systems that can generate meshes for you. But if you start trying to feed it raw Tango data, you're going to find that you've got mathematical routines that simply don't have enough information to know what to do with it. It's true that the more data sets you collect from Tango, the easier things will get. That'll be part of my closing topic. However, you're going to find that a lot of routines that otherwise are amenable, like Delaunay triangulation, get very, very confused when they're dealing with multi-axis data, and you have to do an enormous amount more work. Your first interest in triangulation routines, therefore, is not in building a mesh. It's because they will tell you what the neighborhood looks like. In other words, they will give you the topology. It is the absolutely vital first step in order to doing any other data processing. Finally, in conclusion, let me back up here for a bit. You'll notice that the candlestick is fundamentally invisible, but if you look closely right in this area here, you'll see certain spiking in the image. Also, the image, if you were to dig through it, you'll find it's a large number of visual artifacts. Clear surfaces that both reflect and refract light tend to throw a lot of noise into Tango images. The only reason I observe this is because I buy Google's story of one of the things Tango is great for is navigating around public spaces. However, public spaces can often be stuffed full of great big glittering glass chandeliers. which, as far as I can determine, are Tango's worst enemy. It hates them even more than it hates Mebius strips, which are kind of fun to feed to it.